time we want to rotate the shape that we have here around the line, the y-axis. Here's the origin, here's the y-axis. We're going to rotate this triangular shape around the y-axis. Try to visualize it in your mind, and then we'll see what it looks like. Now from here it looks like a cylinder. If we tilt it up this way, sure enough it looks like that on the bottom, but notice that the triangle had a point to it, and it's got to have gone somewhere. And if we look in at the top of this, if we can see we get a cone-shaped hole down inside that cylinder-like shape, and we want to calculate then what the volume of this cylinder with a cutout of a cone inside of it would be. We can do this with calculus. Each cross section here, and the cross section in the middle, will be the shape of a donut. There'll be the outer circle that we see here, and then there'll be the inner circle, which is the cutaway of that place where the cone comes. And then we take all those levels and multiply them by a dy, and we would be able to get the volume of the cone when we integrate it. Well, let's look this time at what would happen if we revolve our famous shape here. Y equals 2x, y is 0, and x is 1, this bounded blue shape, if we revolve it around the y-axis. I hope you're starting to get some schemes of how you would go about setting these up when you're on your own. I always try to think of the shape revolved 180 degrees and then use my imagination to see what the intermediate things would be. So if you imagine this revolved around the y-axis, when it gets 180 degrees, you're going to see that it's going to be like this. That'd be with the cross section again. But this outside line would have revolved all the way around, and as we saw in that 3D modeling, it's going to look like a cylinder, and it's going to have a cone-shaped cutout on it. So if we try to think of a cross-section going against that, we'd see that we would get a larger circle and then a smaller circle. And if we could find the area of one of those cross sections, which is going to be pi r squared. Why am I drawing with the mouse when I could be drawing with a pen? Pi r squared minus pi r squared, the larger one, minus the smaller one. You're saying, why are you drawing so messily if you're using a pen? And if we integrate that, and we see, since we're cutting a cross-section this way, we're dealing with dy's, and our boundaries then would be y boundaries from 0 to 2. So we have to get the radius of this bigger circle, then minus, and looks like the bigger circle is constant all the way up, and it looks like it's pi 1 squared because it's 1. And the smaller circle is the one that changes with at each cut. It's down here, it's getting close to 0. So it's going to be the x of our equation. And again, the x of our equation has to be given in terms of y. So it's 2x is equal to y, or x is equal to y over 2. So this distance here is going to be y over 2. So this is going to be minus pi y over 2 squared. This is what we're going to integrate. So let's See if we can't clean that up a bit. So this is going to be the integral from 0 to 2 of pi minus pi times y squared over 4, and we had to have a dy here, dy, and if we integrate that, it's going to, let's take the pi completely out here, because then that would make this a 1 and this a 1. So we would get pi times 1 dy would be y minus y cubed over 12. This, with the pi multiplying both of those, evaluated from 0 to 2. At 0, again, the lower bound is 0, so we only have to calculate this at the upper bound, so it looks like it's going to be pi times 2 minus 8 twelfths, which would be 2/3. Is that right? Pi, and this would be, if we put this 24 12, well, no, we don't want to change it to 12, so we want to change this to 2/3. This would be 6/3 minus 2/3. Looks like it's going to, minus 2/3, it's going to be 4/3 pi for the volume here. Sorry that that math is so ugly. Why don't we do that again, because it would be smart to do that, because that would be hard for me to follow. So let's erase this, take it from the top one more time, and deal with the fractions in a more grown-up manner. So, and maybe we can make the thickness of our pen a little bit better too. It'd be good. So we're going to integrate this pi outside, and we're going to replace this 2 minus y cubed would be 8 over 12. And right here we should reduce. 4 goes into 8 2 times, 4 goes into 12 3 times. Now we have to get a common denominator between these two. And so that's going to be 2 is 6/3 minus 2/3. Looks like it's 4/3 pi for the volume of our weird shape, the thing that looks like a cylinder with a cutout cone. Hope that's clear. See how with the cut we had to use a dy. When we were revolving around the x-axis, we used a dx. You should practice some more problems. I should practice some more problems. Have fun. Bye.